This is the end, my only friend, the end of Unit 3, and technically AP Precalculus because we only do the first 3 units on the test. So that's exciting news. Today we're going to talk about polar graphs and polar coordinates and polar bears. That's just a joke. I'm just joshing you guys. We're not going to really talk about polar bears, or are we? What we are going to talk about is polar coordinates versus rectangular coordinates. You're used to rectangular coordinates. Rectangular coordinates are given to you as x, y. Like for example, the point 4, 8 means you go right 4, you go up 8, you put a dot there, easy peasy lemon squeezy. Polar coordinates, though, are given to you as something completely different, r and theta. R is going to be where you draw your dot compared to 0, 0 on a polar graph. Now, 0, 0 is also called the pole. So if R is 3, you're not going like right 3. You're going to count 3 units away and get ready to draw the dot. Where do you draw that dot? Well, your theta is going to tell you where you draw that dot. See, theta is the same theta that it's been all unit long. If you were to go counterclockwise from the right positive axis, or in this case, 0. If I tell you to draw the point 3 pi over 2, then you go to pi over 2 and you draw the dot 1, 2, 3 units away. Simple. Now, what if I want to switch between the two? If I want to turn something that is rectangular into polar, okay, like into polar, what I do is in order to turn my xy into r theta form, the r is going to be found by taking the square root of x squared plus y squared. And if you're like, that's kind of like Pythagorean theorem, it sure is, because your radius is basically you taking the x and the y value and finding your radius, which is kind of like your hypotenuse. To find your theta, you're going to inverse tan the y over x, which again comes very much from SOHCAHTOA and stuff like that. So that's how you would turn something that's rectangular into polar. How do you turn something that's polar into rectangular? Well, it's a little bit friendlier, I guess. R is going to be, or the y value is going to be r cos theta, which should look familiar. The y value is going to be r sine theta, which should look familiar. So if I gave you, what's the point that I used? I think I said 3 pi over 2 or something. Let's just say I wanted you to graph 3 pi over 4. Okay? This tells you how far away you're going to draw that dot from 0, 0, and this tells you where you're going to do it. Pi over 4 lives there. Here's 0, 0. 1, 2, 3, put a dot there. Now, what would that look like on a regular XY plane? Well, let's turn polar into rectangular by doing 3 cos pi over 4 and 3 sine pi over 4. Okay, cos pi over 4 is root 2 over 2. So this becomes 3 root 2 over 2, or 3 root 2 over 2. And sine pi over 4 is also root 2 over 2. So this also becomes 3 root 2 over 2. And if you were to run to your calculator and find out what 3 root 2 over 2 is and pretend that you're going to draw that on an XY coordinate plane, you would land somewhere up here, which is going to be the equivalent to that guy over there, which no one said anything. I put my dot at the wrong spot. It should be right there because I said pi over 4. This whole time I could have been wrong, but I wasn't. Let's move on to the next thing. All right, I moved my face because now we're talking about complex numbers and polar coordinates. Now, complex number involves imaginary numbers. Complex numbers are usually given to us in the form a plus bi. So let me give you an example of a complex number. 2 plus 2i. If I wanted to graph a complex number on a complex number plane, it's very similar to a rectangular plane. You would basically say, you are the real number, so let's go right 2 on the real axis, and you are the complex or imaginary number, so let's go up 2 on the imaginary axis and put a dot at what appears to be 2, 2. Now, if I wanted to link this to what polar coordinates look like, it's going to be very different. A polar coordinate that is also complex is in this form: r cos theta plus I r sine theta. And you might look at this and say, well, wait a minute, r cos theta is like the x value, and r sine theta is like the y value. So and when we graphed this, that was basically the x value, and that was basically the y value. Now you're getting it. By the way, other teachers might write it out like this, where they factor out the r. It's the same exact idea, but it all depends on the teacher that you might have. It's the same. It's all the same. Don't be surprised if you see either option. Now, this was the complex number form. What if I want to make this polar? Well, we're going to do what we did in the other slide, but kind of opposite, where I believe I gave you polar and we turned it rectangular. Now I'm giving you something that looks more rectangular, and we're going to turn it polar. Okay, so when I did that in the previous slide, what I wrote down is, in order to find the magnitude, the r, is we would take this square root of x squared plus y squared. Well, now we're viewing it as a squared plus b squared. And if you're like, isn't it just the same thing? It is. You're my a, you're my b, which is basically like an x, which is basically like a y. So we would say that r is going to be 2 squared plus 2 squared. R is going to be 4 plus 4. R is going to be the square root of 8. And you can clean that up by making that 2 root 2. Now, what we saw in the last slide is, in order to get the theta version of it, we would take the inverse tangent of y over x. Well, I don't have y over x, but it's the same exact idea if we said b over a. Okay, and that gets us our theta. Now, in this case, to save some room, b over a is 2 over 2, so the inverse tangent of 2 over 2 is the same thing as the inverse tangent of 1. The inverse tangent of 1, we technically have 2 answers, but since this guy lives in quadrant 1, we only care about the quadrant 1 answer, which is pi over 4. So my theta is pi over 4. My r is 2 root 2. So in order to take these two pieces of information and make it look like one of those, I'm going to make it look like the blue one because I use that much more often. I'm going to say that this complex number written as a polar coordinate is now going to look like 2 root 2 cosine theta, which is pi over 4, plus 2 root 2. Let's attach an I there, not inside the square root because that wouldn't make sense, sine pi over 4. And what that would look like graphically on a polar coordinate is, you would imagine what 2 root 2 is. So, 2 point something, 3 point something. I actually don't know the answer. And then you would go to where pi over 4 is in that direction. And if this was a polar graph, you would count out 2 root 2 and put a dot there, which would kind of equate to that. Okay? All right. Fun. All right, using trig graphs or tables to make polar graphs. Now, you can memorize what polar graphs look like when graphing polar graphs, and we'll kind of talk about what they could possibly look like as we do problems here. But to me, the best way to draw out a polar graph is to either make a trigonometry graph, like on a regular rectangular plane, or to draw out a table on a rectangular plane using the information that you have. Okay, so let's just say that I gave you something like let's say I want you to graph on a rectangular or on a polar graph r equals 3 cosine theta. Okay, and I want to graph that. A very quick way of doing this, and keep in mind too, AP Precalculus is going to have a lot of multiple choices. So if this is a multiple choice problem, this will be a lot faster than what you expect. But if I were to go and draw the whole thing out, this is how I would do it, okay, quickly. And we will do a lot of these, so don't worry. But a very basic way of doing this is, that 3 cos theta is going to be up 1, 2, 3, down 1, 2, 3. Cosine goes like this and stops right there, regular frequency, so at 2 pi. So it bottoms out at regular pi, at half a pi is where we hit 0, at 3 pi over 2 is where we hit 0 again. Okay? And then we repeat the process. So maybe we draw the points that we know. Okay, at 0, 3, I can go over here and say, all right, well, when theta is 0, I have 3, so the magnitude is 3. So we go over here, and where theta is 0, we have a magnitude of 1, 2, 3, and we put a dot there. Then let's put a dot at 0 on pi over 2. Okay, now what this is going to look like graphically, okay, what this is going to look like graphically so far is as I go from the angle 0 to pi over 2, my magnitude is getting smaller. So what's happening is as I go from 0 to pi over 2, I am going towards this dot. So this is being created. Let me do a better job. One more time. As I'm going from the angle 0 to pi over 2, my magnitude is getting smaller according to this picture here. So I'm creating more like a circle because I'm now heading towards 0. Okay? As I go from pi over 2 to pi, I'm hitting -3. So pi is -3. So if pi is -3, usually regular 3 would be over 1, 2, 3 right here. But if it's -3, it's over there. So I'm literally creating a circle again. And then as I go from pi to 3 pi over 2, it's the negatives. So I'm creating that circle. Okay. And as I go from 3 pi over 2, I'm hitting pi again. So this should be a little bit more circular. So let me clean this up a little bit. This should be a lot more circular. But basically, by using this picture, I am able to draw out what this graph looks like, which is just supposed to be a circle, which I just simply cannot draw. Much better. Okay? All right. Not pretty, but we'll do more. Let's jump into some problems. Given the complex number, graph on an imaginary axis. All right, if I remember what an imaginary axis looks like, okay, let me scooch this up. Because I know exactly where this is going to live. This is my real axis right here. This is my imaginary axis right here. The real number is 5, so 1, 2, 3, 4, 5. The imaginary number is -5, so 1, 2, 3, 4, 5 in the negative area, and we get a dot right there. Okay? Okay. Rewrite in the form r cos theta plus ir sine theta. All right, so very much what we did a couple slides ago. I need to label u A and label u B, and r is going to become the square root of a squared plus b squared. So r is going to equal big square root 5 squared plus -5 squared. Don't worry. It's just going to become 25 plus 25, which is going to become 50, which is going to become factor out of 5 root 2. So that's the r. The way we find the theta, and my lights just turned off in my room, is the inverse tangent of b over a, y over x. In this case, the inverse tangent of -5 over regular 5, which simplifies out to the inverse tangent of -1. Now, the inverse tangent of -1 has two possible answers, one that lives up here or one that lives down there. We want the one that lives down there, which means we are going to have an angle measure of 7 pi over 4. Took me a second there. So putting this all together, we can write out 5 root 2 cos 7 pi over 4 plus 5 root 2 I sine 7 pi over 4. Given the polar coordinate 3, 5 pi over 6, graph the polar coordinate. Easy. 3 is your magnitude. Okay, 3 is how far away from the pole, 0, 0, you're going to put that dot. So 1, 2, 3, or 1, 2, 3, whatever. 5 pi over 6 is going to be the direction that you do that in. So let's locate 5 pi over 6, and let's count out 1, 2, 3, and that's how you graph that. To write that in rectangular form is found by doing r cos theta, very familiar, r sine theta. R is 3, theta is 5 pi over 6, so 3 cos 5 pi over 6, 3 sine 5 pi over 6, cosine pi over 6, let me see, we're over here, is going to be negative root 3 over 2. All right, yep. 3 times negative root 3 over 2. And sine 5 pi over 6 is going to be a half, positive a half. So 3 times a half. So simplify this out, and you get negative 3 root 3 over 2 and 3 over 2. So if you were graphing that on a rectangular plane, you would go whatever number that is, left that many, up a little bit, and you'll have a dot there, which should, if you were to glue that on top of the other, would look just like that. All right. All right, another wardrobe change. It's 6:30 a.m. in Norristown, Pennsylvania. I'm about to do some polar graphing. Wish me luck. Graph this polar coordinate negative 4 pi over 3. All right. Well, this is my magnitude. This over here, right here where I'm drawing that R, and that is going to be the angle that I use. Usually what I do is I go to that pi over 3, which is somewhere around here, and I would draw at 4. But this is negative 4. So what this means is I go to pi over 3, and I go in the opposite direction 4. So I go down 4 pi over 3, 1, 2, 3, 4, and I put the dot there. So a negative magnitude means I go to that angle and I spin my magnitude in the opposite direction than what I'm used to. So basically, if I wanted to, I could rewrite this guy as regular 4, add pi to that, and it would be 4 pi over 3, and it would be the same exact thing. So graphed. Now, to rewrite that in rectangular form, I'm going to use the old r cos theta, r sine theta thingamathing, and plug in what I know. It doesn't matter which one of these I use because they're the same thing. So let's just use the negative original version. So negative 4 cos pi over 3, negative 4 sine pi over 3, cosine pi over 3 is a half, so negative 4 times a half, and sine pi over 3 is root 3 over 2. So since I'm running out of space, let me just write this all in one thing. Negative 4 times a half is negative 2, no overthinking there. Negative 4 over 2 is negative 2 up top, so negative 2 root 3. So if you were to graph this on a rectangular plane, rectangular planes look like this. You would go left 2, down negative 2 and a third, or root 3, whatever that looks like. You'll have a dot right there, which correlates to that dot right there, as if you were to draw an XY axis right there through the pole. Fun. All right, things get a little hectic here. Now, I'm going to do exactly what the directions ask me to do and draw this by making a table. When I'm done, I will explain kind of like a shortcut to do this, where maybe it won't help with drawing, but it will help with identifying, like on a multiple choice test, and that would make life a little bit easier. Okay, so at the end of this problem, I'm going to compare 4 sine 2 theta to a sine or cosine n theta. We'll get there. Right now, I want to graph this by making a table. Okay, so what I'm going to do is I'm going to graph, I'm going to make a table. It's going to look like this. Hopefully I give myself enough space. I'm graphing all the way from 0 to theta to 2 pi. The fact that there's a 2 in front of theta means that things halfway through start to repeat. Since the frequency is 2, that means things start to repeat themselves halfway through. Okay, so by putting a 2 in front of pi, that cuts my normal period of 2 pi in half, because 2 pi over 2. So again, things repeat themselves. So I probably, if I put a theta here, I'm going to use every single number here all the way up through pi. And if I have space, I'll maybe even do the extra one. So I'm going to start at 0, pi over 12, pi over 6, pi over 4, pi over 3, 5 pi over 12, pi over 2, 7 pi over 12, 2 pi over 3, 3 pi over 4, 5 pi over 6, 11 pi over 12, and pi. And I barely just made it. And at that pi, though, I'm going to see the repeating process take place. What I'm going to do in the middle here is I'm going to write out 4 sine 2 theta, and I'm going to allow this to be an area where I do a little bit of calculations. In other words, 4 sine 2 theta is going to be 4 sine 2 times 0, which is 0. And then I'll figure out what that math is over here when I get to it. This becomes 4 sine 2 times pi over 12 is pi over 6. 4 sine 2 times pi over 6 is pi over 3. 4 sine 2 times pi over 4 is pi over 2. And again, as we do these are now more manageable things that we can deal with. We know that we can do all of these signs. We just have to multiply 4 when we're done them. 4 sine 2 times pi over 3 is 2 pi over 3. 4 sine 2 times 5 pi over 12 is 5 pi over 6. 4 sine 2 times pi over 2 is pi. 4 sine 2 times 7 pi over 12 is 7 pi over 6. 4 sine 2 times 2 pi over 3 is 4 pi over 3. 4 sine 2 times 3 pi over 4 is 3 pi over 2. 4 sine 2 times 5 pi over 6 is 5 pi over 3. 4 sine 2 times 11 pi over 12 is 11 pi over 6. 11 pi over 6. And 2 times pi is 2 pi, which is the same as 0. Time to do some math. Sine 0 is 0. So 4 sine 0 is 0. Sine of pi over 6 is a half. So 4 sine of a half is 2. Okay. This becomes 2 root 3. This becomes 1, so 4. This becomes, oh, no way, 2 root 3. Okay, because it's root 3 over 2. 4 times root 3 over 2 is 2 root 3. This becomes a half, 2. Sine of pi is 0, so 4 times 0 is 0. This is negative a half, so negative 2. This is negative root 2 over 3. No, this is negative root 3 over 2. So that would be negative 2 root 3. This is negative 1. Yep. So, yep. Yeah, it took me a second there. So that's negative 4. And some of you might be able to see the pattern forming. This is negative 2 root 3 because it's the same as this. This becomes negative 2 because it's negative a half. And now we're back to 0 again. And then it repeats the process, it repeats the process, it repeats the process. So from here to here, we get these gross numbers. And then if we were to write all the way back around, you would literally just cover the numbers that you would have. So I think we're all right. I think we're all right, but we'll see. Let's graph what we have. 0, 0 is a dot in the middle. Okay. As we move around, you go to 2. Okay. 2 root 3 is going to be like somewhere around here-ish. Okay, and then we hit 4. And then 2 root 3 again. And then 5 pi over 12 is 2. Okay. Then we hit 0. And then for u, we're at negative 2. So that's going to be here. Okay. And then negative 2 root 3 puts me around here. And then negative 4 is going to put me right around here. Negative 2 root 3 puts me around here. And then negative 2 puts me around here, and then back to 0. Now, as we go for the rest of them, we use these same exact numbers in this order. So pi is 0. 13 pi over 12 would be 2. Okay, so here. And then that 2 root 3, and then that 4, and then that 2 root 3, and then that 2, and back to 0. And then here at 19 pi over 12, we would be at negative 2. So that would put me here at regular 2. And then at 2.5-ish, did I go too far? No. And then at 4-ish. And then at like 3.5-ish, not 2.5-ish. And then at 2 again. And then back to 0. So the direction and the trip that I took around this whole thing had me start here. Okay. Loop around here. Okay. And then continue my path around here. And continue my path around here. And then continue my path around here. Now, that was the long way of doing this. Okay, that was the long way of doing this, and it took some time. But what we created here was a rose. And a rose is something that looks like this form. Now, here's something that you can memorize for when you have to deal with this stuff without having to draw it out. Like for example, if I see this, I now know what this looks like, and I know what all of the other A sine and thetas look like. They're going to look like flowers, okay? When n is even, what's going to happen is you're going to have 2n petals. In other words, since I have 2n, I created a rose with 4 petals. If this was 3n, well, hold on. If n was 6, I'd have 12 petals. If n was 4, I'd have 8 petals, so on and so forth. Now, if n is even or odd, I would have that many petals. When it's sine, okay, the flowers do not go through, they don't start here. When it's cosine, the flowers would start here because of the fact that cosine starts at like 0, 1, or in this case, it would be 0, 4. Okay, so a sine would be literally the exact same flower with the petals going through the major axes. But since this is a sine to n, we can expect having the flowers or having the petals go through like the diagonal axes and have 2 times more petals than that number there. So that's like the shortcut multiple choice way of doing a problem like this. Pretty intense. Now, knowing what we know and knowing what we just said, okay, when it was sine, what was it, 4 theta? Okay, we had a flower, sine 2 theta. We had 4 petals and it looked like this. That's awful. Now that we know that this is cosine, we can expect 3 petals where the 1 petal is going to live right there. And so probably have something that looks something like this. That's what we can expect, where these go out to 6. That's what we can expect. So if this was a multiple choice question and we see a picture where there's a petal there, and a petal diagonally here, that's going to be our guy. But that's not what it's asking us to do right here. So what I am going to do is I'm not going to go too crazy. I am going to use, since I know I'm going to get 3 petals, maybe I can just make my life a little bit easier and only do, well, let's see how many I can do. Let's make a table again. Okay, let's make a table again. We have theta, we have 6 cos 3 theta, and we have r. So let's choose 0. Let's choose pi over 12. At some point around here, I can expect repeating to take place. So maybe I stop at 3 pi over 4 if I have room for it. Let's do pi over 6, pi over 4, pi over 3, 5 pi over 12, pi over 2, 7 pi over 12, 2 pi over 3, and 3 pi over 4 is basically all the room that I have anyway. And that's when we will start seeing things repeat itself. Okay? 6 cos 3 times 0 is 0. 6 cos 3 times pi over 12 is pi over 4. 6 cos 3 times pi over 6 is pi over 2. 6 cos 3 times pi over 4 is 3 pi over 4. 6 cos 3 times pi over 3 is pi, so we're halfway through. 6 cos 3 times 5 pi over 12 is 5 pi over 4. I don't know why that took me so long. Maybe it's because it's 6:50 a.m. 6 cos 3 pi over 2. Almost there. 6 cos 7 pi over 4. 6 cos 2 pi. So 0. So now we start repeating. So this will be the same thing as 6 cos pi over 4. All right. Okay. Cosine 0 is 1. So 6 times 1 is 6. Cosine pi over 4 is going to be pi over 2. No, root 2 over 2. So this becomes root 2 over 3. You're 0. You're negative, so negative root 2 over 3. You're negative 1, so negative 6. You're negative root 2 over 3. You're 0. Your regular root 2 over 3. And then the process repeats. So 6 root 2 over 3. All right. So 6, 0, 6. 1, 2, 3, 4, 5, 6. Root 2 over 3 is really small, like point something, like like right here. Okay. 0. And then at pi over 4, which is you're at negative root 2 over 3. So pi over 4 is like u. Okay, and then at pi over 3, we're at negative 6. And then come back down to here. And then 0. And then 7 pi over 12 is here. And then 2 pi over 3 is 6 here. And then wrap back around. So basically, and I have one more. I have, oh no, I'm good. All right. Oh, I do have one more. It's gonna happen right here. Okay. All right. So I start out here. And then I wrap around. Oh gosh. Oh golly. Oh my gosh, by golly. It's a Christmas song. Yeah, so definitely not the prettiest thing in the world. But it is a rose. It's a 3-petal rose. It's supposed to be this rose. This petal looks awful. I should have moved it around a little bit more so that it looks more like this. But again, you guys aren't paying me for my art skills. You're not paying me at all. But I do get money. I do get money, as rappers like to say. So here's my 3-petal rose, just as I predicted. But again, I would look at something like this and say, it's a 3-petal rose because you're odd. I know it starts on the x-axis because it's cosine. So it's not gonna, it's gonna be, rotationally symmetrical. So I should expect, if you're gonna have a rose here, it's kind of like a sideways Mercedes symbol or Mitsubishi or whatever car you like. Because I don't know anything about not cars. Windmill, fan blade symbol. All right, now that we've made a couple polar graphs by making tables, maybe this is less tedious. Maybe not. But what I'm going to do is I'm going to sketch what this looks like on a regular coordinate plane and find a way to translate that on a polar graph. So let me do that right now. We have 2 plus 4 cos theta. Now, cos theta as a regular period of 2 pi, so that's good news. But this amplitude and the fact that we're adding 2 to it tells me we have a vertical shift with a positive 2 change. So we're gonna have a midline here at 2, and I'm really not going to give myself enough space. So let's go 1, 2, 3, 4, 5, 6. That should do it. 1, 2, 3, 4. That's going to overdo it. Let's add one more for funsies, and we're going to have like a midline here at regular 2. Okay. The period is 2 pi, like I said before. So that's going to happen. Magic's going to happen at pi. And then we have 3 pi over 2 and pi over 2 and yada, yada, yada. The amplitude is 4, which means normally at cosine we start at 1. And in this case, we'd start at 4. But since we're adding 2 to everything, we're going to start way up here at 1, 2, 3, 4, 5, 6. Is this 6? 2, 3, 4, 5, 6. And then we're going to hit our midline at pi over 2. We're going to bottom out at negative 2 at pi, hit our midline again at 3 pi over 2, and start the process at 2 pi. So me, drawing a bunch of dots because it looks better than trying to draw for real because I'm sloppy. Now let's label what we know. At 0, I'm at 6. So here's 0, 1, 2, 3, 4, 5, 6. At pi over 2, I'm at 2. So here's pi over 2, and here's 2. At pi, I'm at negative 2. So here's pi. Negative 2 is going to live right there. And at 3 pi over 2, which is this guy, I'm at 2. So 1, 2. Okay. So what's going to happen is as I'm normally on a regular trig graph on this picture, as I move towards pi over 2, my number goes closer to that 2 value. So here I am. My number is going to go closer to that 2 value. So basically we have a picture that kind of looks like this. Okay, now this is where it gets weird. At some point after pi over 2, I hit 0. So this is going to happen. Then I hit negative land, and then I finally hit that guy right there. So this pattern continues, and I create this weird curl going in. Okay, now that I'm at pi and negative 2, I'm going to start moving closer to 0 and eventually hit that 2. So the opposite happens here. Okay. And very similarly to what I saw over here, now that I'm at pi, 3 pi over 2 at 2, I am moving further away and hitting that 6 value. So this is going to kind of create like a circular looking thing here, and I'm going to have this. Now, what I have, and if you are somebody who speaks French, I apologize for what's going to happen. But what I have here is a limaçon. That is like a weird C with a curve on it. Now, I don't speak French. I think it means heart, but I don't know. In America, we call this a cardioid because it kind of looks like a heart. It kind of does. I don't know. But what makes this special from the other two is the fact that I added a number to it. So the number that I add, the number that I could subtract, is going to make this guy look like a specific type of cardioid or limaçon. There's ones that's more of like what's called a dimpled version, and then you have this version. It all depends on what number this is and what number that is. That'll tell you what you're going to get. Okay, but these are examples of what polar graphs could look like. All right, now that we have a little experience graphing these things the old-fashioned way, let's try to memorize what they look like. At the very beginning, we graphed a circle. I believe it was something like 3 cosine theta, and it ended up looking like a circle over here. First things first, a circle is going to be something in the form r equals some number times either sine or cosine. Okay, sines open up here. Okay, if this a was negative, it would open down here. Now we'll explore that. What does the a do? Well, if I make the a bigger, it just makes my circle bigger. Okay, if I make the a bigger, it makes my circle bigger. If a was negative, it shows up down there. What if this was cosine? All right, well, let's change that. Let's change this to cosine. And now it shows up lefty-righty instead of uppy-downy. So a negative cosine appears on the left and a positive cosine appears on the right. And I think we did something like 3 cosine theta to start out the day. I don't remember. Now, what if I were to take a number and multiply it to theta? Well, let's see. If the number is 1, we have that circle still. As the number increases, things explode. Now, we're not going to worry about decimals, not unless we're using a calculator. When it's even, as you know, we double up on the amount of petals that we get. When it's odd, we get the same amount of petals. So something like, 3 cos 3 theta has a rose with 3 petals on it. If I turn cosine into sine, it kind of shifts a little bit. And instead of starting here on the positive x-axis, it starts up here now. Okay, and as I make n larger, so now it's even again, I have 8 petals. If I make it 5, it now has 5 petals. If I make it negative, ooh, it's upside down. And the a just determines whether or not I have something that's bigger or smaller. It's my magnitude. Now, let's bring this back down to 1. Make it a circle. And let's take a look at the limaçon version of it. If I were to take like 1 and add 1 to this, there it is. It makes that limaçon. What if I make it 2? It makes it bigger. What if I made A and made that smaller? It becomes the dimpled version where now it's more of a heart instead of the weird loopy looking thing, which I believe is called a looped limaçon, and that's a dimpled limaçon. So turning it into sine would make it look, it is sine. Turning it into cosine would make it the sideways version. And there you have it. Okay, so you're looking at 3 different versions of these things, and we looked at all of them. Something that's a circle is going to be, 5 sine theta. Something that's going to be a rose is going to be like 3 sine 5 theta. And if I add a number to it, that's where we get the limaçon. All right, now that I'm done graphing those guys, for now I think, let's do something a little different. Trace the part of the graph that covers just one part of the interval. So I have r equals 8 sine 4 theta. So 4 theta gives me the 8 petals. That 8 tells me that this goes out to 8, which appears to make sense. It checks out. I care about tracing the part between pi and 3 pi over 2. So this is what I'm going to do. I'm going to approach this a little differently. I'm going to graph this guy out. Now, what this means by having the 4 in front of it is my period is going to be 2 pi over 4, which means my period is half a pi. So whatever this does is going to repeat 4 times every 2 pi or every half pi. Now, I only care about the stuff that happens between pi, which is u, and 3 pi over 2, which is u. Now, normally I'd start, at 0, 0, and then I'd go up to 8 and down and repeat the process. Up to 8 and then down and then repeat the process. But since I only care about this, I'm going to try to draw this out to the best that I can. Go up to 8, down, repeat. So between pi and 3 pi over 2, I start at 0 at pi. So here I am at pi. Okay, there's my pi. I'm starting at 0. As I go towards 3 pi over 2, what's happening is I'm going out to 8, then coming back, and then normally here I'd go like this, but now I'm in negative land. So what's going to happen is I'm starting at pi. We're in positive land according to my picture. I go out to 8. So let me make this a little bit bigger. I go out to 8. Let me make this a little bit bigger. I go out to 8, right? And then I hit 0. Now on the picture, here I am. As I continue, now I'm in negative territory, which means not here, but instead here. And that is me tracing. So that is me tracing from pi to 3 pi over 2, this little green area. I traced it. Or for my Spanish-speaking friends, I 3'd it. That's 3 different languages we have going on in this one. We had French, we had Spanish, and now we have English. And it's going to stay that way because I'm not that talented. Let's get the pen back to normal. Plot on a complex plane. Well, this is a complex polar point. The old CPP. What this says is I have a magnitude of 2, and I go to 4 pi over 3, which is u, and I go positive 2 in that direction. 1, 2. There. That's what it looks like. The absolute value, if given a point on a complex plane, or a point in general, is the distance from the pole to that point. Well, if I give it to you in complex form, the absolute value is just simply the magnitude. If I give you something in polar form, the magnitude is your absolute value. Absolute value just means distance. So if I give you something in rectangular form, the distance might mean something else, like using Pythagorean theorem or the distance formula. But in this case, it's just the magnitude. So writing this in rectangular form is me accidentally doing what I kind of said we would do. All right, now in rectangular form, what you're going to do to find out your number is you're going to do, and again, it looks like this, a plus bi. Okay, that's the rectangular form of a complex number because we have that I there. The a is going to be r cos theta, so 2 cos 4 pi over 3. My b is going to be r sine theta, 2 sine 4 pi over 3. Okay. So my a is going to be 2 times cos pi over, or 4 pi over 3, which is negative root 2 over 2. Okay, and we can kind of see that down there. And we can kind of see that since it's in the middle of everything, the numbers seem to make sense. So these cross out and you end up with negative root 2. Okay, let me scooch that up. So A is negative root 2. A is negative root 2. Now the B is going to basically be the same thing. And since the numbers seem to check out, this is going to be 2 times negative root 2 over 2. So b is going to also be negative root 2. Now, putting this all together and wrapping it up in a little bow, I need to make it look like this. So we are looking at, and let me put it up here, negative root 2 minus I root 2. Okay, which means, we would go left like 1 point something and down 1 point something, and that seems to check out. Root 2 is 1 point something. And that seems to be exactly what we need. Ugh. Find the distance from the pole, the origin, to the point on the curve when theta is pi over 4. So there's that formula. Not too bad. I know I owed it before, but it's not too bad. All we're going to do is plug in pi over 4 and do a little bit of math. So r of pi over 4 is going to be 2 plus 3 cosine pi over 4. Cosine pi over 4 is root 2 over 2, so 2 plus 3 times root 2 over 2. 2 plus root 3 over 2, and I'm going to leave it like that. There's zero reason why I need to combine that into one term, so that's that. Find the values of theta where there's a maximum value. Now, I now kind of know what this picture is going to look like on a polar graph. But for me, I visualize these better on the regular old trig graph. It's the same thing. If this guy, and I kind of know what the maximum is going to be. I know at some point cosine theta is going to equal 1. So at some point, I'm going to get 2 plus 3 times 1 is 5. At some point, I'm going to get 5. So this is what I would rather do. I know what cosine looks like. And again, now that I kind of said that out in my head, I really don't need to do this, but I'm going to do it anyway. I know that this is going to be vertical shift of 2, so it's going to have a midline at 2 here. It has an amplitude of 3, so it's going to go up to 1, 2, 3, 4, 5. It's going to bottom out at negative 1, and since there's no horizontal shift, it's going to start at 0, 5, and it's going to go down and hit, and then repeat itself at 2 pi. Okay? So common sense would tell me that, again, at some point, and right now, close your eyes and either visualize this, which means you don't have to close your eyes, or visualize the polar graph. At some point, you know your maximum is going to be 5. When's that going to happen? Well, that's going to happen when cosine of theta is 1. When is cosine theta equal to 1? At 1 and only one spot, 0. But since I'm including 2 pi, it's going to happen at 2 pi as well. So my maximum values are going to happen at 0, so theta equals 0, and theta equals 2 pi. Okay? So whether, again, you view that on a polar graph, and I think this picture is going to look something like this, okay, that's going to happen right here at the very beginning, which is a very good place to start. Sound of Music, which I believe took place in Germany, I think, which I believe the German word for no is Nein. It's a shame we didn't have any problems that involved the number 9. There's still time, but 9. No calculator? No calculator. I move my face at everything just to find out that there's no calculator. But again, we really don't need one. Find the average rate of change on that interval right there. Now, it's going to be ugly, but we don't need a calculator for it. Okay, the average rate of change for a polar function is the exact same process for the average rate of change that you saw back in Unit 1. The average rate of change is if I have f of b minus f of a, or r of b minus r of a, you put that over b minus a. So if I called you a and I called you b, then what I need to do is find out what r of 5 pi over 4 minus r of pi over 2 is over 5 pi over 4 minus pi over 2. So I'm going to step to the side here and just, take my time because I'm going to need the space and show what r of 5 pi over 4 is, and then I'll do r of pi over 2 directly underneath that. Okay, so we're going to have 2 plus 3 cos 5 pi over 4. 5 pi over 4 is quadrant 3, so that's negative root 2 over 2. So 2 plus 3 times negative root 2 over 2. So 2 minus 3 root 2 over 2 when you multiply them together. And let's leave it like that, just in case something magical happens in this process right here. Now let's find out what r of pi over 2 is. Pi over 2, how nice. Why? Well, 3 cos pi over 2 is going to be 2. Why? Well, because cos pi over 2 is 0. So now that I have this information, I can replace r of 5 pi over 4 with 2 minus 3 root 2 over 2 in an unnecessary parentheses. So let me just get rid of that parentheses. Now we're going to minus r of pi over 2, which is just 2. So if I had more there, then I'd want the parentheses, but don't need it. Why don't I change this to 2 times 2 so I can have 5 pi minus 2 pi over 4. Now I can combine them. 2 minus 2 go away. So I have negative 3 root 2 over 2 all over 3 pi over 4. Let's multiply the top and the bottom by 4 over 3 pi to get rid of the 3 pi over 4 on the bottom. U2 simplify out to 1 and 2. U3s go away, and that leaves me with negative 2 root 2 over pi. For which polar function does the limit of theta approach infinity of that polar function equal 0? I have 3 polar functions right here. Okay, I need to find the one where the limit equals 0. Well, if this was chapter 1 and I had thetas at the top and thetas at the bottom and whatever, I would only focus on the first term of each. Right? So you would be theta squared over theta, which is theta. And if I plug in infinity, I get infinity. So not u. Does the same rules apply here? Yes. So this becomes infinity, so it's not u. You become 2 root theta over, or 2 theta to the 4th over theta to the 4th. You cancel out, you become 2. Can't really plug in infinity because there's nothing to plug it into, so I get 2. So not u. You're my leading term, you're my leading term. So you become 1 over theta to the 4th power. If I plug in infinity, I'm going to get like 1 over a really, 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 really big number, which is like 0.00000. Oh, it's 0. You're my guy. Makes sense. Okay. Limits with polar functions behave very, very, very similarly as limits and regular functions. Regular. Lots of regulars. It's like I own a restaurant. Lots of regulars. Oh, there you are. Hello, Mr. Calculator. We've missed you. All right, graph the polar function in the calculator. I love these. These are going to be beautiful. Find r of 1.5 pi. So let's graph that in our calculator and see what we get. So part one is to take this gross looking function and find out what 1.5 pi is. Well, before we can graph a polar graph, we have to make sure our calculator is set to polar. So click mode, go down to function, and make sure it's polar, like so. Then what we're going to do is we're going to hit y equals, and we're going to type out this thing right here, 5. Now this is where it gets crazy, so bear with me here. There's no sine squared button, so this is how we're going to do it. We're going to wrap sine in parentheses, so sine theta, completely close it, and then square that. That is the same as sine squared theta. Minus 3, do the same thing for cosine. So wrap it in parentheses, cos theta. Make sure you close the whole thing, so double up the parentheses, square that as well. And then plus 1. Now, let's hit graph and see what we get. Ooh! If you needed to zoom in, you could, but I kind of like what we have. Let's leave it like that. Let's leave it just like that. My job for part A is to find out 1.5 pi. So let's do second calc and type out the value. If you're like, what are those? What are those? Calculus, you'll find out next year. Just hit value. And we're doing 1.5 pi. Second caret gives me pi. Hit enter. And we have 6. Oh, it's actually negative 6. Negative 6. All right, so negative 6. Negative 6. Find the average rate of change on the interval 0.75 pi minus 1.25 pi. So what we're going to have to do is we're going to have to find the values of r of 1.25 pi minus r of 0.75 pi, right? And then we're going to put that over 1.25 pi minus 0.75 pi. So I don't know what the answer is yet. Whatever this is, whatever gross number that ends up being, is going to be over 0.5 pi. So let's see what happens. All right, so let's find the average rate of change of 0.7 pi and 1.25 pi. So we already did the part on the bottom. Let's do the part on the top. Let's do the second thing that we did here and calculate the value of 1.25 pi. And we get negative 1.414214. So let's quit out of this and type that out. Negative 1.414. And then I'll hit minus and I'll do the other part when I get back to it. Let's go back here and calculate value. Now I'm going to do 1.25 pi. Enter. No way. It's the same. It's the same. So since it's the same, I'm going to get 0 up top. 0 over anything is 0. Oh, it's 0. The answer is 0. And it's 0. Graph the function. Is it the same thing? I just want to show it off? Okay. So graph the function on the graphing calculator. So I already did. So I'll probably take a screenshot of the graph and just show it here on the screen. And I'm going to have it right there. And I'm going to talk about it and say, wow, isn't that a cool picture? What a really cool picture that is. That picture right there. What a neat picture. It's like a weird, deformed windmill type picture. But isn't it such a pretty picture? It is. And speaking of pretty picture, that's what you guys are to me. Pretty. And pictures. But this is the end of Unit 3. Why I sang that song at the very beginning. So we're done. We're done Unit 3. Good luck. At this stage, you should be, if you've watched all of my videos, you should be adequately prepared for the AP Precalculus exam, whenever that is for you, probably sometime in May, unless it's a different year and the world has changed drastically. I mean, we just had COVID, so you never know. But thanks for watching my videos, and good luck. Good luck. Love you. Bye.